We also need to know how capacitors can be combined together. The reason is, even if we had a whole lot of money in storage space, we can't buy capacitors of every possible size because they're not produced in every possible size. It's just like cash. Rather than printing bills in everything from $1 to 10,000 or $10 million, it's easier to print a few kinds and have people combine them. First way we can talk about doing this is in parallel. So this means the capacitors have their top plates connected to each other and their bottom plates connected to each other. Here we've got left and right, but it's the same thing. So these four capacitors are connected in parallel, and the set of them is connected to a battery. What single capacitor could replace these four? The easiest way to see the answer to this is to imagine that the four capacitors, which may have very different values, all have the same dielectric stuff inside them and the same plate separation. Then the differences in the capacitance must be due to differences in plate area. So we'd have C1 is A1 epsilon over D, C2 is A2 epsilon over D, etc. Now imagine bringing the capacitors closer and closer together until their plates touch. Now we have essentially one large plate with the area of these four smaller plates added together. So our total capacitance must be A, this total area, epsilon over D, which of course I could write as epsilon over D times A1 plus A2 plus A3 plus A4, but this is the same as C equals C1 plus C2 plus C3 plus C4. This is a general formula for capacitors in parallel. The equivalent capacitance is the sum of all the individual capacitances. This tells us the final capacitance has to be larger than the largest individual one. And we also notice that all the capacitors have the same voltage between their plates, since all their top plates are connected and so are their bottom plates. The general rule is that when things are in parallel, they have the same voltage across them. The other obvious way we could connect multiple capacitors is a chain end to end. This is also called series. We've got three capacitors in series. What is their equivalent capacitance? Now, to figure this out, when we imagine hooking this up, we can expect the top plate of the top capacitor up here to start picking up positive charges from the battery, and the bottom plate of the bottom capacitor to start picking up negative charges. These charges should balance, so we'll have, let's say, plus Q at the top and minus Q at the bottom. What about these four plates in between, the central capacitor and the bottom of the top, as well as the top of the bottom? Well, if you imagine building this, again, it's not an efficient way to build a capacitor, but we could build it out of sheets of metal. This metal piece here, the bottom of the top one and the top of the middle one, that's just a single eye-shaped piece of metal. And we have the same thing here in the purple box. That's an eye-shaped piece of metal. No charges can be added to this or taken away from it because they started out neutral, and we're assuming no electrons can jump these gaps. So if we look at this, whatever charge separation has to happen here, we can have negative charges come up to the top of this because they're attracted by the positive charges on the top plate here, but that will leave positive charges behind down here at this end. Same thing in the purple box. We've got negative charges on this plate outside the box, so we expect positive charges to gather here, which would leave negative charges up here. These charges have to balance because, again, we can't have any charges leaving this eye-shaped piece of metal. We can just have them separate. What this means is the charge on each of these three capacitors is the same, plus Q on their top plates, minus Q on their bottom plates. Even though the capacitances themselves may be very different, the charge has to be the same on all three. Now, what will that do for us as far as solving this? We know that the potential difference between the top plate of the top capacitor and the bottom plate of the bottom capacitor has to be the same as the potential difference on the battery. We could call that V. And we also know that because this works like height, this is kind of like one long ladder and this is kind of like three shorter ladders. If I add up this voltage, and this voltage, I have to get the same as the battery voltage. So I can say V total is V1 plus V2 plus V3. We go back to our main capacitor formula, which tells us Q equals CV. And I can write V total is Q over C effective. So V is V1 plus V2 plus V3. That means Q over the effective capacitance is equal to the sum of Q over C1 plus Q over C2 plus Q over C3. All the Q's are the same, so we can divide them out and get the formula for capacitors in series. 1 over C effective is the sum of 1 over Ci, all the individual capacitances. This is our general formula. What this means is the effective capacitance is less than the smallest individual capacitance. Now, the most common mistake students make here is to forget this final reciprocal. So, for example, let's say C1 is 40, C2 is 60, and C3 is 240 microfarads. I'll see something like this on a test. 1 over 40 plus 1 over 60 plus 1 over 240 is 0.04583 microfarads. This is wrong for two reasons. First of all, the units are not microfarads. I've got inverse microfarads here because they're on the bottom, and if I pay attention to that, I won't make this mistake. Again, people usually leave the units out and just put in what they need at the end. If you keep track of them, it'll stop you from doing this. But anyway, this is really 1 over the effective capacitance. So when I take its reciprocal, I get the real answer, and this is in microfarads, 21.82. Now, what would we do if we had some horrible looking mess like this collection of many capacitors? How could we find the single capacitor that would replace these? The way to do it is in small bytes. We use these same series and parallel principles. These three capacitors, for example, we'll call them 1, 2, and 3. They're all in series, so I can reduce them to a single capacitor we'll call A. 1 over Ca is this sum of 1 over each of the capacitances. I solve for Ca and get 54.55 nanofarads. The next two, the 400 and 500, they're in parallel, so they're easy. I just add them and get 900 nanofarads, and I say that is Cb. This next one is by itself, so there's no point giving it a letter. We could just leave it as C6 and say it's 600 nanofarads. And finally, these last three are in parallel, so we add them. So we call that capacitor C. It's the sum of these. It's 2400 nanofarads or 2.4 microfarads. Now we redraw the circuit with these new capacitors A, B, and C. These four are in series, and we know how to handle that. So we find the equivalent single capacitor. 1 over C equivalent is the sum of these reciprocals. We solve for that and we get 46.455 nanofarads. That means this is our equivalent circuit. Obviously much simpler. Now we can make our way back out. We know Q equals CV, so we can find the charge on this capacitor is 557.5 nanocoulombs. That's what I get if I do this times 12. That also means that the charge on all of those capacitors that were in series is 557.5. So A, B, 6, and C all have that same charge. That lets us find the voltage on each of the first three, because if Ca is 557 nanocoulombs, so is 1, 2, and 3. These are all the same as their total, Ca. So I know that Q1, Q2, and Q3 are all 557.5 nanocoulombs. I know Q equals CV, so I find the voltages. 5.575, 2.787, 1.858. For capacitors 4 and 5, we figure out what the voltage across that pair is by putting in the value for CB. We calculate 0.619 volts. That's the voltage across both number 4 and number 5. Now that will let me find the charge on number 4 and number 5 because, again, Q equals CV. So I multiply, I get 247.8 nanocoulombs on the smaller capacitor, 309.7 on the larger. Notice that if I add them together, I do get 557.5 like I'm supposed to. For number 6, V6 is this 557.5 nanocoulombs over 600 nanofarads, 0.929 volts. Finally, what about the bottom three capacitors? Again, I find the voltage by dividing the charge by the total capacitance. I get 0.2323 volts. Now I find the charge on each of them individually from Q equals CV. And I get 162.6, 185.8, 209.1 nanocoulombs. If I add all these up, Surprise, 557.5 nanocoulombs. What would we get if we added the voltages? We can't add the same ones multiple times. So for example, I can't take the voltage across this capacitor, which is the same as this and this. I can't add those three together because it wouldn't make any sense. It's one voltage across all of them. So if I add this voltage and this one and this one and this and this and this, if I add those, what do I get? V1 plus V2 plus V3 plus VB plus V6 plus VC, 12 volts, like it had to be. Now, the charge stored on a capacitor represents potential energy. We could and we do extract that energy to do work. What's the energy stored in the capacitor? Well, we know that moving a charge Q through a potential difference delta V means we have to do work Q delta V. But as we add charges to the capacitor's plates, the delta V will change, so this means we need to do an integral. W is the integral from 0 to our final voltage of Q dV. Now, we know Q is a function of V. It's simple. It's just CV. So we plug it in and we get a very simple integral. 1/2 CV squared. This tells us the energy stored in the capacitor. Now, it turns out capacitors aren't really great for energy storage, but they are great for power storage. The difference is we use the capacitors for things like driving the flash in a camera. The reason is the battery contains a lot of stored energy, but it can only release it as fast as its chemical reaction can happen. The capacitor, on the other hand, can release energy much more quickly. So we use the battery to slowly charge up the capacitor, and then the capacitor quickly dumps all that energy in the flash. That's why you have to wait a second after you use the flash before you can use it again. And you see the same thing in the defibrillators in movies and TV shows. You have a battery that charges a capacitor, it shocks the patient's heart, and then they have to wait around for a few seconds before the battery will charge up enough to let them shock again. This ability to discharge and charge very quickly would make capacitors much better than batteries for electric cars. They could be recharged faster than you can fill a car with gas even, if you have a big enough power supply, and there's not really a limit on the number of charge and discharge cycles. As far as speed, the car could be as fast as the motors would allow. The motors would be the weak point, so it could be faster than a Tesla. The problem is energy density. To figure that out, we need to do stored energy divided by volume. If we're still using parallel plate capacitors, we know the volume. It's A times D. So we plug that in this formula, and we can write that this energy density, notice that's a lowercase u, 1/2 epsilon A d V squared over AD. I can do a little rearranging, and then I remember that the voltage difference divided by D is the electric field, so I can say the energy density is 1/2 epsilon E squared. Now, Wikipedia says supercapacitors currently have an energy density about 10% of what lithium-ion batteries have. That's too small to be competitive because that means your electric car would only go maybe 20 or 30 miles. Things may change pretty soon, though. Capacitors are used in the regenerative braking systems because if you have an ordinary car, you step on the brakes and it converts your car's kinetic energy into thermal energy, mostly at the front brakes, which you can get out and touch your front wheels if you want to verify that. Electric cars, on the other hand, when you step on the brakes, the motors in the wheels act like generators and they charge the battery. They can only do this so fast. They may have to turn some of that energy into heat as well if you stomp on the brakes at 70 miles an hour. Capacitors could absorb that energy pretty much as fast as the wheels could deliver it, though, and then they can slowly trickle it back into the battery, kind of the reverse of the camera flash.